not Sark. Sark, guess I always forget which one.
Hey guys, so real quick, if you guys haven't checked your announcements, the announcements I do on web course, I recommend go checking because I'm going to host an exam review. You guys have an exam next week. So I'm going to be doing an exam review tomorrow, okay? I had to make a few changes. I wanted to do it next week, early next week, but some stuff happened. I need to do it tomorrow to accommodate best for you guys and for the other physics sections as well. This time, the exam review will be fully online, okay? So it's going to be on Zoom, and it's going to be at 10 a.m. tomorrow. That's where my regular SI sessions hours are. If you can't make it, don't worry, it will be recorded. It will be recorded and posted along with the solution. So you guys have more than a week to go and watch the recorder as many times as you guys want. But I definitely recommend attending the review because then you can ask me questions and I'll be going over the questions as well. So the exam review is going to be tomorrow at 10 a.m. Okay? The problem set has already been posted and the links to the recording and to the problems that are already posted in the announcement. So go back there, check all the information is there already. You guys are going to receive a few more announcements today and tomorrow. So just keep an eye on that. It's a great resource for the exam. Dr. James checked the problems that we're going to go over. And so it's a good opportunity in extra space. So I hope you guys come to the exam. Thank you.
Yeah. All right, y'all. So I'm actually glad he's doing the review sooner because honestly, sooner gives you a sense of, might give you a better sense of what things you do or do not know how to do. It's better to know that sooner than later in a lot of ways. I have already gone ahead and yesterday I was able to make a draft of your all's exam. So at this point, I have a decent sense of what it's going to look like. I still need to do some polishing, double check, all that kind of stuff. But with that in mind, the current structure that I'm thinking of, the current setup for it is 16 multiple choice and then 3 free response. Now, when I say 3 free response, each one is one part. It's not like last time where it was 2 free response, we each had 2 parts, so it's effectively 4 free response. So, a little bit less free response. Instead of you solving 4 free response problems, you're just solving 3. And there's one more multiple choice question, and the reason I added that extra multiple choice question was just to make the numbers work out nicely. So previously when there's 4 free response, I make them each worth 10 points, that adds up to 40 points, works out really nicely. 3 multiple choice, 3 free response do not divide nicely into 40. So what I've done is I've adjusted it so that the free response is now worth 36 points instead of 40. 3 times 12 is 36, nice round numbers. And that means 64 points, and 16 divides nicely into 64. So that's the logic there. The one quote-unquote extra question I've added, so I'm still going to make sure that time-wise it goes fairly smoothly, but I will tell you all, make sure you can do right-hand rules. Right-hand rules show up. Obviously, we've been doing them again and again and again. We have done so many practice ones on that. And this is just a further reminder, you need to make sure you can do the right-hand rules, because my gosh, they show up a good enough for the test. Because direction matters. Direction matters a lot. It's way different to move right than to move left. So right-hand rules have to do with that directionality. And I would say maybe 30% of the questions, maybe 40%, that's somewhere in between, involve right-hand rule in some capacity. That's why I'm telling you all, make sure you can do right-hand rule, because if you cannot, it will not go great for you. I'm going to make the review sometime in the next few days. The goal is to have that done before the weekend, so that I can post that for you all, and that review is what we'll go over on Tuesday. So that's the dream there. Otherwise, I think that kind of covers it. I'll also take all the clicker questions, and I'll make a PowerPoint with all the clicker questions in them again. That's easy enough to do. But I think that's it. Any quick questions about the exam or anything about that? All right, one last thing. AC circuits are not going to show up. In fact, it might seem like we're not going to have time for AC circuits at all, which is very sad, especially since I made the entire PowerPoint slides on it. But plan is we're going to finish up Faraday's law kind of today, and then we're going to do inductors. We're going to talk about inductors, which are just solenoids used in circuits. So that'll finish up this week. So there's not going to be AC circuits in the exam. The exam will be DC circuits. It will be everything to do with magnetic fields that we've been learning about, forces due to magnetic fields, what makes magnetic fields, Faraday's law, which is how to make electricity with the magnetic fields, inductors, and then after test 2, we'll just focus on light. We'll have 3 days, and we're going to focus on light. We're going to learn that light is, you probably heard this phrase, electromagnetic wave. If you just think of the 2 words there, electromagnetic, a light is an electric field and a magnetic field that oscillate, that are a wave. So we had to cover electric fields and magnetic fields to talk about light, because light is both things.
I just saw this question for the exam. Since it's only going to be 3 responses, is the point distribution changed?
Yeah, so it'll be 36 points for the free response, 64 points for the multiple choice.
Yeah, but I mean, like, you said you get a range from like 1 to 3 points for a picture.
Yes, I will make a new rubric instead of 12 points instead of out of 10 points. Yeah, it'll shift slightly. Yeah. The values will kind of stay the same, it'll just.
The values will just.
Yeah, the values will kind of shift. Yeah. So there's 4 free response choices, you'll pick 3 of them. Yeah, so there's 4 free responses that'll be put there. One of the reasons there's only 4 instead of more is that a point that I didn't think about is the more questions I give you as options, the more you have to read, and that actually takes time to evaluate. So there's going to be 4, and I'll also tell you each one comes from a week worth of content. So one of them comes from DC circuits. One of them comes from forces on magnetic, moving charges or current wires. One comes from sources of magnetic fields, and one comes from Faraday's law. So, 4 questions for the 4 major topics we covered. You'll pick 3 out of those, whichever 3 you're strongest on. And the rubric will follow the same structures before, just expand slightly. Yeah. Sorry. Yeah. The next exam is next Thursday, November 6th, I believe. Yeah, November 6th. Note cards are up here. I'll put some more out here as well if they run out, but I'll have them today and Thursday and Tuesday next week. All right, so let's finish up Faraday's law. I'll still have office hours and all the normal things there, but let's scroll on down. All right, Faraday's law. So what we learned last class, where is it? It's actually way here at the beginning. Is that when you have a changing flux, it makes something called an EMF. Now, I told you all when you see EMF, just in voltage, because it works the same way. But we call it EMF because it is slightly different, but it functions the same way. So, changing flux makes an EMF, makes a voltage. If we have a voltage, we then have a current. So that's what we talked about, and then we said, hey, what are the 3 things that can change? Magnetic field, area, and the angle. So, I showed kind of those 3 scenarios. We did a few examples. We changed the area. We said, hey, if you have multiple loops, then you got to chuck an N in front of it. So I updated the equation to have a capital N for the number of loops, if there is multiple loops. We did one with a changing field. Now, in this case, it was uniformly changing, meaning it was linear, meaning we didn't have to worry about the derivative. Then we talked about what if it was rotating, and this is something that's very important for you all to understand, is rotating objects, because the world is full of, even though it doesn't look like, a periodic motion is something very, very important. That's actually why we're going to spend the week and a half on electromagnetic waves, is to continue to reinforce periodic motion. And so, we talked about the variables you all need to remember for rotation, specifically angular frequency, angular velocity, 2 words for the same thing. That's omega. That's the rate of change of the angle. And then we talked about regular frequency, which is how many rotations per second, or how many revolutions per second. Same thing. And we see the conversion between the 2. So we then derived to go from cosine theta to go to angular velocity and then to regular frequency. Angular frequency, the regular frequency. And then we use that to derive the expression for a rotating object in an this is the EMF generated by such. So this is an important thing for you all to know. In my opinion, this is the most important kind of EMF that you all need to know, specifically because this is how generators work. Generators work by spinning things, and this is the equation that describes it, and this in turn generates AC current, AC voltage. So this is the rotating object. Make sure you all know how to do this. Like, make sure you are comfortable with this whole cosine sine thing. Yeah.
For the review that's happening tomorrow at Wednesday, where's the link for that? Because I'm checking the start thing at the only.
Ask me at the end. I'm not sure actually. That's a geek question. He'll be able to answer that at the end. All right. So we talked about what happens when you change the frequency, and we found that it makes the voltage higher and it makes the voltage change more quickly. It changes the amplitude and it changes the period. Period is the time it takes for one full cycle. And that's where we ended. So, real quick, I don't think I showed you all this, but this is a fun thing you can we didn't really have the time to show you this, but this is just a proof. Maybe I did, maybe I didn't, I don't remember. But just to remind you all, this is a generator. This is what they look like. Look, a rotating coil in a magnetic field. And we get in this case, a cosine wave for the voltage. And if I make the rotation slower, it makes the amplitude smaller, it makes the period larger. When I make the rotation quicker, it makes the amplitude larger, it makes the period smaller, i.e. it oscillates quicker. So great, it proves it. Now, I say it proves it. This is literally just using the equation that we just derived. So it's just a visualization of the equation that you all derived. Yeah, and you can play with this yourself if you want. It's good. All right. So yeah, we definitely did that. And then we talked about the direction of current. This is actually where we left off. Lenz's law. We talked about the negative sign. We finally looked at the negative sign. And the negative sign tells us that the direction of this voltage, which in turn makes a current, is opposite the change in flux. So we then, Lenz's law, and there was kind of this three-step process. And this is kind of wordy, but we summarized it pretty simply. Are you making more or less field lines, and in which direction? Counteract that. Make field lines to counter the change. And then the current will be in the direction. We'll use right-hand rule 2.5 to find the direction. So we're going to do a few more examples. We didn't quite finish all the examples, so just to kind of recap a few of them. I'll remind you of this one from last time. So I have a loop that's coming down. As the loop enters this, so I'll erase this down here. As the loop enters this region of magnetic field that's pointed out of the page, I'm getting more magnetic field out of the page. As it moves down, I get more dots. Great, why do I care? Counteract the change. How do I counteract more dots? Make more in the other direction. How do you cancel vectors? You make them in the other direction. So we're going to make a magnetic field into the page. How do we make a magnetic field into the page? Point your thumb into the page, curl your fingers, and that's going to be the direction of current. Something I do a terrible job of in this class is demos. Like, I haven't done any demos. It's something I know I'm bad at. Thursday, I will attempt to actually bring some demos because there's some really cool This is how regenerative braking works as well, which is kind of cool. And there's a few other cases of it, but that's the one that's most practical.
How do you know it's more V out and more V in? How do you know it's more or less?
Yeah, so think of as this loop moves down, at some later time, the loop is down here. When it's down here, it's got more dots. So therefore, I have more magnetic fields inside of it that are pointed out on the page. We're counting field lines. More field lines means stronger field. Yeah, so we're going to keep practicing some more. This one, I know the contrast isn't good here, but there's a bar moving to the right. I want you all to think about the first step. Don't shout out the answer, think about it. Am I getting more field lines or less field lines? And which way am I getting? Am I getting more in or more out? Am I getting less in, less out? Think about it. So the key here is the loop is formed by this. It's the closed loop. So as this moves to the right, am I getting more or less? Think about it. And then you can do the other steps if you want to jump ahead.
Current's not V.
Mm-mm. Yeah, good question. V is velocity of that rod. All right, so as this moves to the right, did I get more dots or less dots? If it moved to the right, previously I had about 6 dots inside it. When it moves to the right, I have 8 dots inside it. It seems like a silly thing, but that is sufficient to understand this.
Why isn't it, I thought you meant dots inside
The loop. No, yeah, that's a good question. It's the dots in the loop, not the dots in the rod. It's all about the loop. I'm getting more B out. Counter it. How do I counter a bunch of extra arrows out? I'm going to make more in. How do I counter? If I'm making more out, then I need to make B in. I need to cancel out those dots. How? Make some field that's into it. How do I make a magnetic field into it? Right hand rule 2.5. Thumb in. Clockwise current. So this is going to be a make I clockwise. This is the answer. This is the thing I'm looking for. Question A. So question A here is the exact opposite. Question A, just to connect to the question was, can you re-describe question A? I'm happy to do so, because question A and question B are the exact opposites. Question A, the rod is moving to the left, so I'm getting less B out. How do I counteract less? I make more of them. So basically, if I'm getting more of the field, I cancel it. If I'm getting less of the field, I make more of it. Those are the two possible scenarios. The third scenario is nothing changes. So either there's being more and I need to counteract that, or there's being less and I need to counteract that. All right, now this one, nothing is moving, but what we need to think about here, it says B is increasing. When B is increasing, the way we draw these diagrams is the more dots there are, the stronger the field. The less dots there are, the weaker the field. That's a common way to draw these things. We call it the density of the field lines. So, as B increases, which way is B currently pointed in this picture? Y'all can shout this one. Out of the page. If B is increasing, am I getting more of those or less of those? Great, it's exactly what you think it is.
Wait, how do we even know that it's pointing off the page?
Dots mean out of the page. X's mean into the page. Blue dots, that's out of the page. That's notation. So I'll write that to the side. Dots mean out. X's mean in. All right, so I'm getting more B out. Counter it. If I'm getting more B out, how do I counter more arrows out? I'm going to make some B in. How? Right hand rule. Thumbs pointing in the direction of the field I'm making. What's making that field? The current. Steps 2 and 3 are kind of happening at the same time. I'm making a field in. What's actually making the field? Current. The field isn't making the current's making the field. That's just a conceptual thing there. So I'm going to make a current, in this case, clockwise. All right. Now one last one, and then I'm going to give you all some problems to practice this.
Sorry, so it's getting more B out because
B is increasing.
it's like the strengthening.
Yes. Stronger the field, more arrows. Weaker the field, less arrows. All right. Here, something very important is my area vector is pointed up. This loop is not flat on the page. It is, I don't know what you would describe this as. Yeah, perpendicular to the page. It's like looping out of the page and then looping back into the page. It's very hard to draw that, so I just drew the area vector for you all. Yeah, it's like a coin sitting flat on a table. Yep. And then the field here is going out of the page. In this case, the field is decreasing. I'm going to let you all think about this one. All right, this one I needed to grab a cable so I can actually show you all a loop of this. So here I just grabbed a random cable. It's overkill, but it does the job. Here, my coil is like this. It is flat, like sitting on flat on the table. Which way? But the magnetic field is pointed like away from my chest. How many of the field lines are going through this circle? 0. So as B decreases or increases, I go from 0 to 0. Did I gain more or less? No, nothing changed. It's to make sure you're being careful. It's all about the flux. In the back of our mind, this is flux that we're working with. So what is the flux? So in this case, am I getting more or less? Nothing. Like, I'm not getting more or less. Nothing's happening. So what's going to happen? Nothing. So what's going to happen after that? Nothing. I am not getting more or less field lines through this because I get no field lines through this to begin with. I don't care how much that field increases. It's not going to change that. If I rotated this, then it would be a different story. It all has to do with again, you can think of this like a flow. Think of these like arrows flowing through it. Think of it like if I wanted to blow a bubble, no one's blowing a bubble through a wand that's perpendicular to your breath. It just doesn't work. So, great. There's that scenario. All right, let's see if any of this landed. You all have to these are problems that you just got to do a bunch of practice ones of, like everything I've kind of taught you in this class. Practice, practice, practice. All right, it doesn't want to respond to me, so I'm just going to close it, reopen it. So, now we're just going to practice it. That's kind of the main emphasis today is practicing this and applying to some problems. A loop of wire flat on the page. When I say flat on the page means like that. Starts in a place of no magnetic field. It then enters a magnetic field pointed into the page. Which way will current flow? So this is, I will tell you the answer is not 0. This is not one of those situations. So, draw this if you need to. It's helpful to draw it. I will draw it to help us understand this. Draw where it starts, draw where it ends, go through the 3-step process. Am I getting more or less? And in which direction? Counter the change. Which way will current be generated to make that happen? All right, maybe over about 20 more seconds. All right. In 5, 4, 3, 2, 1. All right, so we're just going to draw a picture of this. Pictures are great. Here's where it starts. There's nothing. Here's where it ends. There's something. Specifically, there's a field pointed into the page. So then we go through our process. Did I get more or less? I got more B in. You can see I had none, now I have some. That means I gained more. 2, counteract that. Make B out. How do you counteract getting more in? You make B out. So we're going to make some B out. We'll just call them like dots. Counteract the change. How do you make that happen? Right hand rule, thumb out of the board to make it, and that's going to be counterclockwise. So, how many field lines do I have in this situation? How many field lines do I have in this situation? I have 4 of them. That's more. Are they in or out? So there you go. I got more. B stands for magnetic field. I have more magnetic field lines in.
How are we like assuming that we're supposed to just like put some in?
It then enters a field pointed into the page. You have a beginning and an end. The problem describes those 2 things.
So wait, if it had no magnetic field, would the answer be no current then?
If it went from a place of no field to no field, then nothing happens. It's got to change. The flux has to change. The number of field lines have to change. And this is one possible way. Why did they increase? Who knows? Actually, this is an interesting tangent. You all have probably seen enough movies to hear about, and you probably read about this. When a nuclear bomb goes off, they have the electromagnetic pulse, and that damages electronics. Now you all know why. What happens when a nuclear bomb goes off? It makes an electromagnetic pulse. What is an electromagnetic pulse? It's a very strong electric field, magnetic field, that spreads out from it. In fact, it oscillates. I now have no field. I started with no field, and then all of a sudden this really high intensity field comes in. I went from no field to a really strong field. What will that cause to happen in every single loop of wire that interacts with? A current. Your phone is made of a bunch of tiny, tiny little wires that are not able to handle large currents, and they're built as such. This will induce a very strong current in your phone and every other electronic device, and if they're not built to handle that much current, which most aren't, it fries it. So this is why electromagnetic pulses are dangerous, is every single loop of wire will experience a large current sporadically, unexpectedly. This is also a problem with solar flares. If you have a really, really, really strong solar flare, it also is emitting a strong changing magnetic field, and that has the same problem. If it's strong enough, it can actually penetrate through the atmosphere and destroy everything. And fun fact, every single set of wires we have, if there's electricity flowing through it, it's a loop in some capacity. So every power line, every electronic device, even if you turn it off, it's still going to experience this current. It doesn't matter. We have no current flowing through here. There is a changing field. So it's actually quite tricky to protect your devices from this.
It's kind of a random question, but like, are magnetic fields like the reason like water flows the other way?
No, that's a good, the reason the water flows, that's the Coriolis effect. It has to do with the rotation of the Earth and the speed of the water on it. But yeah, so that's a practical application of this, why things break.
If you have like a more complex circuit, like imagine a loop with like the line going through the center. Would you have to like use Kirchhoff's laws or like
Yeah, if you had a really complex circuit with a bunch of loops, you'd have to find the areas of each loop and things like that. It does become quite complicated. But this is fun facts for you designing electrical engineers and things like that. You have to account for these. Because what makes magnetic fields? Current-carrying wires. What's your phone full of? Current-carrying wires. So your current-carrying wires make fields that induce currents in other current-carrying wires that are right next to it. And if you have really sensitive currents, really low amounts of current, that can actually be significant. So, fun fact, everything's inducing current and everything else in some small amount. And it's something you actually have to account for. No, it has to have a flowing current in it. All right, to connect this to permanent magnets, and there's only a couple of things I need to tell you about permanent magnets to help you answer this. I have the north pole of a magnet moving towards a loop of wire, as shown. If you're looking at the loop from above, will this make a clockwise current or a counterclockwise? What I need to remind you all of is that magnetic fields point away from the north end of a magnet. You need to know that. The magnetic fields point away from this north end. They point towards the south end. We don't care there. And also, you need to know something that I assume you're all very comfortable with. The stronger you get to a magnet, the stronger the field. That's something you all, when does a magnet stick to a fridge? When it's close. So, using those 2 pieces of information and what I've taught you, find the direction of current. When I have a north magnet heading down to a loop, will the current go counterclockwise or will it go clockwise? Or 0? I'm getting less field lines down, less field lines up. The magnet is approaching the loop. The magnet is approaching the loop. All right, we got 20 more seconds on this. All right, in 5, 4, 3, 2, 1. All right. First step we're going to do is draw a picture. Why? Because it's good for us. Which way do the field lines point? Due to a north magnet. They point away from the north magnet. They point down. They technically loop back around, but we don't care about that. We just care what it's doing around the loop. So they're all kind of pointing down. Even the ones that are kind of angled, they're pretty much down. Great. They're pointing down. I'm just going to draw a couple of them. I'm not going to put 5 of them there because that gets a little messy. As that magnet approaches, so I'm going to draw a second picture off to the side. So boom, there's that. It approaches. Now it's closer. So we know we have field lines pointed down. We can see that in our original picture. The question is, do we have more or less? When it gets closer, we're going to have more. Why? Because it's stronger. The field is stronger the closer you are to a magnet. That's not a hard thing to convince you all of. Again, you played with magnets. You've experienced that. The visual way to explain that is the fields are doing this kind of thing. They're spreading out. So as you get closer, you kind of capture more of those field lines. So long story short, let's go through our thing. We get more B down. Depending on your perspective. If you're looking down on it, yeah. In this case, we'll say down just to match the picture. Yeah, you could do it from that perspective. Yes, yeah, that's more than 5. I'm getting more B down. How do I counteract that? I'm going to make B up, which would be, that out of the page. How do I make magnetic field lines up? So I need to make some field lines up to counteract that. Put your thumb up. Which way is that current going to go? Counterclockwise. When viewed from above, that is counterclockwise. So there you go. 3. So make I counterclockwise when viewed from above. Counterclockwise. All right. Surprising amount of things in this, but these are good to practice. Yeah. Yeah, it's a great question. How close does it need to get? If it moves even a tiny bit, current will be induced. It doesn't have to. And it'll induce it all the way up until it gets all the way up here. Now, as it starts to go through it, it gets more complicated. As the magnet starts to pass through it, it starts to get more complicated. Fun connection for you all. If y'all ever seen those flashlights that you shake them and they charge them, this is what they're doing. Have y'all ever played with those flashlights that there's like a little thing in it and it shakes up and down and you can charge the flashlight by doing that? This is literally what you're doing to charge the flashlight. You are making a magnet pass up and down through a loop of wire, and it induces a current in it.
So, for a straight wire, this doesn't happen, correct?
Yeah, great question. For a straight wire, you won't get a current. I'm going to tell you that. That is a great question that we'll answer at the end of this PowerPoint. It's a great question. The question was, does this happen for a straight piece of wire? And my answer is, you won't get a current, but something will happen. And we'll see that at the end, but we'll have to build to that. But I appreciate you asking that because that segues nicely. All right, one more. This one is I have a magnet. Now, the magnet here is stationary, and I have a loop of wire. Now, this loop of wire is spinning. How is it spinning? It's spinning like a steering wheel. That's my best description I can use for this. It is not spinning like a coin. It's spinning like a steering wheel. So take this loop and spin it like a wheel. Like a steering wheel. That's the best example I can give for this. You can kind of see it in the picture. It is not spinning like a coin. It is spinning like a steering wheel. It's just going in the one direction. So this thing is, if you imagine like a hula hoop, it's is not spinning like a coin. That's the best thing I can tell you all. It's not flipping around like that. It is spinning like a steering wheel in one direction. Which way will the current be? Clockwise, counterclockwise, or no current? And my coil is spinning, for those in class, it's spinning like this. Exterior, what do you wonder? My own is spinning. Yeah.
Where's above the magnet?
Huh?
Where is above the magnet?
There is no above the magnet. There's a magnet over here to the side. So the magnet, if this is my coil, my magnet's like here.
Yeah, but I mean, like which side are you looking at?
Oh, it's the north side pointing.
Okay, so the north side's closer to you?
The north side is closer to the loop, but the magnet is not moving. All right, 24 seconds. All right, in 5, 4, 3, 2, 1. All right, so we're going to draw our field lines. They're going to point away from the north, so they're going to kind of point through this magnet or through this loop. Now, as my loop spins, am I getting more or less of those or no change? No change. Just because this is spinning, I'm not getting any more. Imagine that I was like blowing through this thing. Imagine my breath was like a magnetic field. If I blow through this loop and I spin it, I don't get more air through it. Now, if I rotated it like a coin, it would be a different story. But it's not rotating like a coin. That's why I stressed that a bunch of times. As I rotate this object, nothing changes. Rule of thumb, if you close so like in this situation, I had it, you looked at it, you closed your eyes and I rotated it, you opened them. If it looks identical, then nothing's going to happen. It's a good rule of thumb. If it looks the same as when you open your eyes and close, then probably nothing changed. So 0. 0 amps. Just to be more official. But yep, 3-step process. No increase, therefore nothing happens. All right. Now, we're going to prepare for this problem. This is a toy problem. It's not like you're never going to see this in the real world, but it helps us prepare for a later problem. That's the whole point of this. I have a kind of a weird system here, and we've seen this a few times now. I've used it a few times. We have this kind of wire setup where we got this rod that's free to kind of slide along it. It can slide left, it can slide right. The right side of this is open. The left side is closed, and there's a resistor in it. So, for now, the question is, what is the flux through the current loop? The first question you have to ask yourself is, where is the loop? The loop is a closed path. So where is my loop? Boom, there's the loop. It's a closed path. The other side is not closed. The other side goes to infinity. So that's not a loop over there. Great. Find the flux. Not the EMF, not the voltage, not the current. Just find the flux. So back to the first thing I taught you on this PowerPoint. Find the flux through that. Nothing is moving right now. It will, but for now it's not. There is an equation for flux, so this is seeing if you remember it. It was one of the first things we learned in this PowerPoint. You have to go back and And we're looking for magnetic flux, so that should hopefully be obvious. All right, give y'all about 20 more seconds. All right, in 5, 4, 3, 2, 1. All right, so we need to remember the equation for flux. Flux is the integral of B dot dA. Now, I told you all in basically every single problem we do, B is going to be a constant. The area is going to be a constant. Dot product turns into, so B times dA times cosine theta. I'm not going to give you any problems where you actually have to do the integral, so those will just all come out. dA becomes A. So I have B times A times cosine theta. Theta is the angle between B and A. In this problem, the angle is 0. Why? Because the area vector is parallel to the magnetic field. How do you find the direction of the area vector? Remember, you just take your pencil, put the eraser on it, and that's the area vector. It can go either way. It doesn't really matter. You can make the angle 0 and 180. I'm not really concerned. We're not going to worry about a negative sign here. And the area here is just L times X. It's a square. So what's the flux? It's just B times L times X. It's B times the area. So this is saying if you all remember the equation for flux. Now we need this. There's a reason we did this. I'm going to go ahead and use this real quick and then we'll find the direction of current in just a second. Remember that EMF is going to equal negative N times D flux dt. So we're just going to plug this in and derive it real quick. dB times L times X times dt, or derivative with respect to time. It's not multiplied by it. My B is a constant. My L is a constant. How do you know that L is a constant? It's the length of this rod. My rod's not getting bigger or smaller in this picture. So pull out the constants. B is a constant. L is a constant. In this case, there's only one loop. So, N equals 1. So I get negative B times L times dx dt. And dx dt is something that you should look at and say, that's a variable that I learned in Physics 1. It's the definition of a very important variable. It's the rate of change of position with respect to time. It's velocity. So what's the flux in this rod? Or sorry, what's the EMF in this rod? BLV. We'll see that's in a future slide, but I just wanted. This is the derivation for it. It's one line. This is something you need to know. I think I put it on the formula sheet. I need to post the updated formula sheet. It's got just this one, I think, and one more.
Wait, but you used the Faraday's law?
Yep.
But you added a multiply by negative n? Or no, positive.
Yeah, that was the updated Faraday's law. Yep, there's a second slide with that one.
Oh.
N is the number of loops. In this case, one loop.
Oh, multiple loops of y.
Yeah. This has one loop. All right. So great. We're going to get a voltage. And if we get a voltage, so if the rod starts to move, I'm going to get a voltage in this thing. If I get a voltage, I'm going to get a current. Which way would that current be? We've done this one a few times. We've seen this one a few times. Now I'm telling you this rod's going to move to the right. So now my velocity is no longer 0. It's moving to the right. Use Lenz's law. Which way will the current flow? Go through the 3-step process. Am I getting more or less? Counteract it. What current will make that happen? Try it out. Will current flow clockwise, counterclockwise, or no current? Yes, the X's are everywhere. That's very important. And they're the same everywhere. So as this bar slides to the right, am I getting more or less field lines in which direction? Counter the change, make a current to make that happen.
I just saw the magnetic field pointing north.
You got to go through the 3 steps. Yep, you got to go through. Am I getting more or less of them? Then counter that, and then find the direction of current.
Counterpart.
As this rod moves to the right, do I get more X's or more dots, or less X's or less dots? That's the first question. Yeah, well, there is no dots, so don't care. Yeah, I'm giving you both scenarios. All right, give y'all about 10 more seconds. All right, in 5, 4, 3, 2, 1. So, let's just draw a picture of what this looks like a little bit later. A little bit later, the rod is to the right. Did I get more field lines or less of them? Which direction? I got more field lines into the page. Yeah, more B in. Why? There's more X's. So, counter that. Make B out. How do you make B out? So we're going to make some magnetic fields to counter that change. I don't want more. Counter it. Out. That's going to make a counterclockwise current. Thumb out, counterclockwise. Counteract the change.
Wait, but what does that even mean? Like, make B out?
I need it. Just how the universe works. As more field lines go through here, this will make a current to counter that change. Why? Well, we'll see at the very end of this PowerPoint we connect it to something, but for now, I'm just telling you it does that. It's a law. Yeah.
Is this for like a real world application? Would there just be like a silver rod moving inside of a wire?
Yeah, that's a good question. Real world application, yeah, this would be like a rod that just slides along. It's a silly problem. It's not a real problem, but we will use it to get to a real problem. I didn't ask you for this, but just a reminder to you all, you could then find, if you wanted to find the value of this current, so we'd use the equation that we just derived from the last problem, BLV. If you wanted to find current, you all need to remember that this acts like voltage. If I have a voltage and if I have a resistance, how do I find current? V equals IR. In this case, we use that epsilon, and you can find the value of current from that. Yeah.
Why was it 0 in the last one? It's not here.
The last one didn't even ask about current. It wasn't moving in the last one. I just derived it. Yeah. All right. Now, I want to draw this current real quick because I need us to draw a picture of this to help understand something. So we're going to get a counterclockwise current for the reasons that we specified. So the current's going to flow as shown, counterclockwise. Something important is this is not free. This is not free energy. I'm not just like, this is not super easy to move this rod. And I want to remind you all why. This is going to be good practice. Actually, I'm going to make this a problem.
I was just thinking more methodically, like that's what I was asking.
Oh, yeah, that's it. Just counteract. The rule is that you're going to counter the change. That's how it's going to go. So, in this situation, we decided the current's going to go counterclockwise. Since the current is counterclockwise, the current will go up through the silver rod. I know it doesn't look silver for you all, but in the actual, when you look at this with a screen, it's silver. Here, I'll color it for you. Now it's silver, maybe. I don't know. Does that make it silver? Great, silver. All right. Why am I telling you this? Since the current is counterclockwise, the current will go up through the silver rod. Find the direction of the magnetic force on this rod. Will it be up, down, left, right? Let's just go with a bunch of random ones. Up, left, right, into page, down, out of page. This is right-hand rule. Current carrying wire in a magnetic field. Find the direction of the force. So we found the direction of current. The current will go up through this rod. What will be the magnetic force on this rod? The force through the magnetic field on a current carrying wire. If you wanted to do, it was just like, if you wanted to do other things, this is what you would do. Alright, I'll give you all about 20 more seconds on this. This is going to be either you know right-hand rule at this point or you don't. This is right-hand rule number 1. Force on a current carrying wire. Right-hand rule 1 was force on a current carrying wire / moving positive charge. Same thing. Second one was the magnetic field due to a current carrying wire. And the third one, quote unquote, was a shortcut for the second one. If you have a loop of wire, you can find the magnetic field inside of it by doing the whole spinning your hand. So basically there's 2 rules. One for force on a moving charge. The other is magnetic field made by a moving charge. I taught it a different way than like this, but that is one way of doing it. Yeah, there's a bunch of different ways to do it. Yeah. All right. 3, 2, 1. All right. So it is always useful to draw things. So the current is up. So I'm going to point, the way I taught you all is you point your fingers in the direction of current. This is for the direction of positive charge moving. Current is positive charge moving. I then need to swing that arrow in the direction of the field. Which way does the field point into the page? So your hand can only close in one direction. Make it close in the right direction. You point your fingers up, you swing them into the page, and the force is to the left. Why does this matter? This is the magnetic force on this wire. So this rod is moving to the right. If you want this to move to the right, you need to pull it to the right. But as you pull it to the right, you are actually going to experience a force opposing that motion. The magnetic field, if this was a physical thing and you pulled this thing to the right, you would actually feel it pulling against you. It would not be free. You'd feel the resistance to you pulling it. You'd feel a force trying to tug it in the other direction. Why? Because current carrying wires, this will generate a current, and then by generating current, there'll be a force on it. Because there's a force on it, you'll feel that. For what? To find the force on it? That's right-hand rule number 1. So whatever version of right-hand, force on a moving charge. That's a great question. Which field do you use? The field it's in. Yeah, you do not use the field that it makes, because the field it makes does not affect itself. Rule of thumb, if something makes something, it doesn't affect itself, with the exception of solenoids. You see that clearly.
So when you move the current carrying wire, is the magnetic force always opposite of?
Yeah, that's a great question. When you move a current carrying wire, if there's a loop like this, yes, the force will always be opposite, because it's going to oppose you. It's not free energy. It's not trivial to do. If it was in the same direction, it'd be helping you, which would mean it'd get exponentially more, which would be kind of wild. But yeah, there's resistance to this. So this is just an important thing. When you're making electricity, there's a resistance to that motion. If you were spinning something instead, you would actually get a resistance to that spinning. And the reason this matters, I think I mentioned this during like the Texas blackout, every single generator is coupled together. And so if any of them starts to lag, it actually starts to put a force on all the rest of them. And that's a problem. They all have to be in sync. Otherwise, they start to experience forces that oppose, and it's not great. Yeah. That is a great point as well. For every force, there's an equal and opposite in this. You can kind of think about it that way. It doesn't, in space, if you pull something to the right, you actually don't run into a problem. So this is specific to making a magnetic field. But yeah, so kind of sort of. The forces. Now, that does get us to the next problem I am going to have you all do, though. All right. This is just a derivation that I already did, BLV. We did this in the previous slide. Now it's in writing. You can see here in the picture we have the applied force that's making it move to the right, and you have the magnetic force that's fighting it. So it's putting all those pieces together in one PowerPoint. All right, now we're going to use this to solve a problem. And this problem is complicated. I don't currently have one like this, but it's a great problem on the test. I say it's a great problem because it really tests if you can put a bunch of concepts together. But I will tell you I don't have one like this because it's actually hard to make different versions of this. It's the same problem, but sideways. And now we have gravity. So I've got a rod that is free to slide, and it will start to slide because there's gravity. Because there's gravity, this silver rod, is going to start to fall. This is also in the presence of a magnetic field pointed into the page. So it's the same problem as the last one, just rotated. And now the reason that this rod is going to start to fall is that there's gravity, and there's a magnetic field pointed into the page. Great. The question is, what will be the direction of the magnetic force on the rod? There's a bunch of steps we have to solve before getting to there. Oh, thanks. I do appreciate that. Okay, it's slightly different than the last one. The magnetic field is out of the page. Thank you. That would change the direction of the forces here. Well, actually, we give us the same answer for A, but it's fine. All right. What will be the direction of the magnetic force in the rod? Okay. Well, force of gravity is going to pull it down. And without doing all the steps, remember, this is not free energy. As this thing falls, it's not just going to be free. There's going to be a magnetic force in the other direction. We're going to prove that in just a second. But we can jump to that if you just remember the last problem. That's going to counteract it. It's not free. Why is it that way? We're going to go through the exact same process we just did. As this falls, am I getting more field lines or less field lines, and in which direction? Yep, I'm getting more B out. As it falls, I'm getting more dots. Counteract that. Make B in. Counteract the change. To make a B in, which way will the current flow? Clockwise. This problem basically puts together all the pieces that I've been teaching you. Clockwise current. Okay. Now, if there's a clockwise current, I actually really only care about the current flowing through this wire. So there's my clockwise current. Do the right-hand rule. Practice it yourself. Fingers in the direction of current. Swing them towards the magnetic field. Which way is the force going to be? And that will answer part A for us.
Why'd you throw that right arrow up?
Because I threw it wrong. Yeah, great catch. That is not clockwise. Thank you.
What's even the point of counteracting and adding those X's?
That's just how things work. As the flux changes, this will make a current such that it counteracts the change. What way will that current? How do I counteract the change? I make field lines in. How do I make field lines in? Current this way. This is just what will happen. Whatever is changing, it will make a field to counteract that.
I was just thinking the clockwise rotation, the arrows, we could still have that without the counteract.
No, that's why they're made. That's the logic. That's our understanding of why it does it. All right. So, right-hand rule. Put your fingers to the left. I need to be able to swing them in the direction of the field it's in. Not the field of me, the field it's in. The field it's in are the blue dots. So I put my fingers to the left. I need to be able to swing them towards out of the page. And we get a magnetic force that's up. Great. So that answers part A for us. Part A, current is left. B is out. Therefore, force due to magnetic field is up. Those three dots are therefore. You've probably seen that in your math classes. If not, it's just shorthand because therefore is a big word.
The magnitude of the force, not necessarily going to be the force of gravity.
Yeah, it's a great question. That also, you're segueing me very nicely to the next one. The question was that force is not necessarily equal. You are correct. It will be equal when we reach a very specific point, though. And that's what we're going to see with part B. Find the equation for the terminal velocity. Yeah, what does terminal velocity mean? It means my acceleration is 0. If you go skydiving, terminal velocity is the fastest you reach. It does not mean you stop moving. Terminal velocity, 0 acceleration, does not mean you stop moving. It just means you stop getting faster.
So it's like the Earth constantly spinning at the same speed.
Yeah, kind of, sort of. So the important thing for part B, I'm going to take this picture, I'm going to steal it over. And there's just one more thing we need to get through, so we're doing fine on time. If you're concerned. We only have inductors left to cover, and inductors are just solenoids in a circuit. So I'm going to steal this, plop it here for part B. Part B, I want to find the terminal velocity. Now, to find terminal velocity, what does terminal velocity mean? Velocity max equals question mark. Now, it's something very special. When you reach this, you stay there. So when you reach terminal velocity, your acceleration is 0. Don't get the bad habit. A lot of people do this. Just because acceleration is 0 does not mean velocity is 0. That obviously sounds crazy. If you're skydiving and you reach terminal velocity, it doesn't mean you stopped in the air. It just means but it does mean something we're going to use here. Yeah.
Is that why like you use your parachute to like slow down at the end?
Yeah, that's a parachute will make the terminal velocity lower, which is good for you. All right. This is probably one of the most important equations that you all need to know is Newton's second law, at least for like any engineering physics majors. F equals ma. The sum of forces equals ma. Anytime we're talking about forces and acceleration, that should be something that comes to your mind. This is one of the most important equations in all of, reality. It's used so much. Build this. What are the two forces acting on my rod? Gravity and the magnetic field. Magnetic force points up. Gravity points down. My acceleration is 0. Because it's terminal velocity. Now you all just need to find these equations. And there's going to be a couple steps here. FB equals ILB sine theta. That's from their second week. That will be on the test. That's one of those things you need to know. We know the length of the rod. It's given in the problem as L. We know the magnetic field it's in. That's B. We do not know the current. How do we find the current? Why is there a current? There's a current because there's an EMF. Remember, EMF equals I times R. Rearrange that. I just used Ohm's law. I equals EMF over R. The resistance is given in the problem. I don't know the EMF. Why is there an EMF? We derive this expression. The EMF due to a rod in this situation is BLV. It's a bunch of steps in this problem, but if you can do this problem, man, you know what you're doing. Remember, anything that's complex is just a bunch of simple steps strung together. Every single one of these simple steps is things you should be able to do. The hard part is stringing them together.
Did we define BLV today?
Yeah, that was from here.
Oh.
Yep. Just to remind you all where that BLV came from. It came from deriving it using the derivative and things like that. So now you just put all the pieces in. And all of this is just asking questions. I don't have this. How can I get this? Now I don't have this. How can I get this? Now I don't have this. So on and so on. So just to put all the pieces together and then see if that helps us. So that means my current equals BLV over R. Put that in here. That means my EMF is BLV. Oh, I already did that for us. I don't need to do that here. Ready to solve for the I? Take this I and put it where the force is. Put it where the I is. That was the whole point of this. So that means my magnetic force is going to equal B times L times V over R times L times B. Theta here is going to be 90 degrees, 0 degrees. No. I always have to think about this. Be careful. 90 degrees. It's the angle between current and the magnetic field. So great. There's my force due to magnetic field. Last step, just plug it in here. You do need to plug in the force due to gravity, which is also something that you all should kind of have memorized at this point. BLV, I'm going to go ahead and combine things. L times L is L squared. V, and then the B times B is B squared. Minus M times G. Rearrange this to solve for V, and you find that V equals mgr over B squared L squared. For the sake of time, I won't be able to spend too much time on this. Like, that was just algebra. Check that out in your own time. I went through it quick, but you can do the algebra. V is velocity. V is velocity. Lowercase v. All right. So there you go. There's that. Feel free to check it out in your own time. I'll post this. I just need to show you all the last example. We have a moving rod. Now I'm going to show you all something kind of interesting. Yeah, this will be posted too. I'll post this immediately following class. So for the sake of time, I won't be able to go through it. If you want to stop by at the end. I just got only 8 minutes, but if you want to come at the end or just check this out later, I just don't have the time right now to chat through it. All right. I've got a rod. I've removed the rails. I've removed the resistor. It's just the rod now. This rod is moving to the right. What happens to the electrons? Remember, there is electrons in this rod. Why is there electrons in the rod? Because it's made of atoms.
Is the rod metal?
The rod, it doesn't actually matter. It doesn't matter whether it's metal or an insulator, but we will say it's a metal. A conducting rod. What happens to the electrons? I'm going to remind you all, I have negative charges moving to the right. Find the direction of the force on them. There's electrons all in this wire, and they're all moving to the right because they're in the rod. So they're all moving to the right. Find the direction they're going to move. Right-hand rule number 1. But they're electrons. I'm not going to tell you why that matters, but I'm going to say it does. They are electrons. And this magnetic field is pointed into the page. So electrons moving to the right, and the magnetic field is pointed into the page. Find which way they're going to get pushed. I am glad to see people are being careful and realizing electrons are significant.
Is this right-hand rule 2.5?
Right-hand rule 2.5 is the magnetic field generated by a current-carrying wire. This is right-hand rule 1, force on a moving charge in the magnetic field. All right, give you all about 20 more seconds. All right, in 5, 4, 3, 2, 1. So this gets back to the question someone asked previously, what if there wasn't a loop? What if there was just a moving wire, a straight wire? The wire does have to move. If the wire is not moving, nothing happens. But if the wire is moving. Now, right-hand rule, fingers in the direction of velocity. Swing them in the direction of the field. My field is into the page. That gives me a force upwards. If you answer that, you're wrong. Because these are negative charges. Negatives always do the opposite. Any rule I teach you, negatives do the opposite. So the force on positive charges is up. The force on negative charges is down. And these are negative charges. Now, let's look at both of these forces though. If I take some these negative charges are going to get pushed down. The positive charges are quote unquote going to get pushed up. What does that mean? This is a conductor. The negative charges will move. They will build up on the bottom. I'm going to build up a bunch of negative charges on the bottom. And if I build up a bunch of negatives on the bottom, I'm going to therefore end up with a bunch of extra positive on top. I will have a voltage between these 2 points. There will be a potential difference between these 2 points, almost like a capacitor has a positive and a negative. So, fun fact, you can actually treat it the same way we treated the sliding rod, using the same derivation. You can pretend like it's moving through space, and you can draw like this loop and do the things. And the voltage it generates is the same, so that's why we did the sliding wire. That's why that problem is useful, is for this one. And you may be like, why do I care? When is there ever going to be a rod flying through space? So they actually did this. They went out in space, they had a satellite, and they made a wire that was like kilometers long. Now, you're like, well, where did the magnetic field come from? The Earth. The Earth makes a magnetic field. You got a spaceship going, and then you got a satellite with a wire going through it. It's the exact problem we just did. This made kilovolts worth of potential difference between it. It was actually high enough that there was some air trapped in the wire, and it was high enough that it actually ionized the air, and it was quite dangerous. It actually broke the wire. There's a video you all can check out about that. There was like a bright flash because the air turned into, lightning. No, it wasn't very safe, but it was a cool experiment that this is one way to generate electricity in space. If you generate a potential difference, you can use that to drive a current. But it turns out it was way too much to handle. It wasn't very safe. It actually sent so much current that it actually wasn't good for the electronics in some ways. All right, and that's kind of it. And there's just a problem practicing that, but it's pretty straightforward. So yeah, practical case of this. Maybe one day they'll try it again. I don't know. It's kind of dangerous though. All right, Thursday we'll do inductors. If you didn't grab a note card, I got them up here. Come grab one. Inductors on Thursday. There will be a couple questions on the test on them, so you do want to be here for that. Thank you. Have a good one, y'all. Make sure you're starting now. Do not wait to start studying. Sooner the better.